Phosphatidic acid synthesis. This is an anabolic pathway that is occurring in the cytoplasm. Bam. Like a boss. What essentially is happening is we are going to make a glycerol molecule. We're going to make a glycerol molecule, and then we're going to attach on not create. We're going to tack on some fatty acids to make a triglyceride. We can also tack on some fatty acids and a polar head group. Polar, Hg is head group, to make a phospholipid. Those are kind of the two main products of phosphatidic acid synthesis. Now, because we are in an anabolic pathway, we are going to get our the precursor for glycerol. In this case, what we're looking for is dihydroxyacetone phosphate from two different locations. We can make it via gluconeogenesis from pyruvate, gluconeogenesis style, or we can make it via glycolysis from glucose. So this was glycolysis. Because we have an excess of energy, we might still be breaking down sugars. If we have too many sugars inside of our body, we can still have an energy excess and still have some sugars there. We can still be breaking them down via glycolysis, even though we already have too much energy. At this point in time, we're trying to store the energy. Our long-term storage form of energy is as a triglyceride. Or in the case of a repairing cell, rapidly dividing cell, any cell kind of requiring some more plasma membrane, we've got phospholipids that can be made as well. So that was glycolysis, this was gluconeogenesis. That word is way too freaking long. At any rate, that is where we're getting our dihydroxyacetone phosphate. Now, we also make dihydroxyacetone phosphate in glycerol recycling in fatty acid breakdown, breaking down triglycerides. This will likely not be formed from that, as we aren't going to be breaking down triglycerides anymore. That would happen within our intestines if we're intaking them as food. If we were to get dihydroxyacetone phosphate via glycerol recycling, it would be from a fatty acid that was broken down in our adipose tissue, and that's not going to be happening right now. Therefore, these are the only two locations that we're going to get our dihydroxyacetone phosphate. It's not from glycerol recycling in the case of triglyceride breakdown. So, what's going to happen to this dihydroxyacetone phosphate is it's going to be made into something that resembles glycerol just a little bit more. What it's going to be acted on, it's going to be acted on by the enzyme glycerol 3-phosphate dehydrogenase. So we're going to write that right here. It's going to be acted on by glycerol 3-phosphate dehydrogenase. And it's going to make, as you may have already guessed, glycerol 3-phosphate. Now, as a quick aside, glycerol 3-phosphate looks a little bit like this. It's basically just 3 carbons linked together with associated hydrogens. Bam, bam, bam. What essentially we're going to do is we're going to take a fatty acid and put it on here. We're going to take another fatty acid, put it on there, and that's going to be our diacylglycerol that we can attach a polar head group to, or we can take a third fatty acid and tack it on there, get rid of the phosphate group. That would be our triglyceride. So that was a wonderful little look ahead. What's going to happen to this glycerol 3-phosphate? Oh wait, 1 second. We have a dehydrogenase. A dehydrogenase requires something. It's going to move hydrogens from one location to another. We have an acetone here. What an acetone is a ketone. A ketone is a carboxylic group in the middle of a carbon chain. So our dihydroxyacetone phosphate will look like this, with the same wonderful compound that we had before. Nope, there would be no hydrogen there because carbon's already formed 4 bonds. It would look like this, and then it would be our dehydrogenase is going to take hydrogens from NADH plus H plus, and it's going to tack those hydrogens onto both the carbon and the oxygen to make this molecule, which is our glycerol 3-phosphate that we just talked about. Again, 2 hydrogens on each NADH molecule, NADH and NAG and H+, which are going to go onto the carbon and the oxygen respectively to create this nice hydroxyl group there. Once we have that hydroxyl group there, we can start adding on fatty acids. So I'm going to make this look just a little bit prettier. This is our NADH plus H plus going to NAD plus. From our glycerol 3-phosphate, it's going to be acted on by an enzyme called acyltransferase. Which is going to do exactly what the name implies. It's going to transfer an acyl group, and it's an enzyme, which is great. The acyl group that we're going to be transporting doesn't need to have a specific length, it doesn't need to have a specific saturation number. What it does need is some kind of energy to attach that acyl group to the glycerol group. In order to form a bond, energy is required. When you're breaking a bond, energy is going to be used. So this acyl that we're talking about here needs to be activated. So we need an acyl-CoA. It's going to release a coenzyme ASH. The hydrolysis of this high energy bond is going to be used to form the bond between acyl and glycerol. So what we're going to be doing here is we're going to be making monoacyl glycerol. That's right, good. We're going to be making monoacyl glycerol 3-phosphate, which is a mouthful and a half. What's going to happen next is this is going to happen basically in the exact same way with the exact same enzyme a second time. Acyltransferase is going to take an acyl-CoA group, remembering that an acyl is any fatty acid that you've got. It basically just needs to be a long carbon chain. It can be any amount of saturation, any amount of unsaturation, and it's going to tack it on to the monoacyl glycerol with the release of coenzyme ASH. Again, the hydrolysis of this high energy bond is going to be providing the energy to attach that acyl group to the glycerol. This is going to make diacylglycerol 3-phosphate. Phosphate takes too long to write out. P with a circle around it is now going to represent phosphate. Now, here is where the pathway can diverge. It can keep going in the exact same path with another acyltransferase. Oh, no it cannot. It can keep going in the same path and create a triglyceride, or it can go in a slightly different path to make a phospholipid. I'm going to erase all of this, and we're going to follow those 2 pathways. So really quickly here. So what we have right now is a diacylglycerol 3-phosphate. And what that looks like is your 3 carbons, 2 of them with fatty acids, and one of them with a phosphate group. Now, because we have this phosphate group here, we can't really attach another acyl-CoA on there. We need to get rid of that phosphate group. So what's going to happen is we're going to have an enzyme is going to act here called phosphatidic acid. Phosphatase. Again, our diacylglycerol 3-phosphate is our phosphatidic acid. So we have phosphatidic acid that's having a phosphatase activity. A phosphatase is going to cleave off a phosphate group, so we're left with diacylglycerol. At this point in time, we're also going to have the release of a inorganic phosphate, which was this phosphate right here. That phosphate gets kicked off by the actions of this phosphatidic acid phosphatase, leaving us with diacylglycerol. Our diacylglycerol can be acted on by acyltransferase again. Again, remembering that we need an activated acyl group, acyl-CoA, because the energy used from that bond right there is going to be used to bind the acyl group onto the glycerol molecule, giving us a triglyceride, or a triacylglycerol. Triglyceride is easier to write, so I wrote that. So this was our first pathway here that went into triglyceride. Let's run through the second pathway that's going to go into a phospholipid. We have our glycerol 3-phosphate molecule right here. When we make a phospholipid, all we're really going to do is attach some kind of polar head group onto that phosphate molecule. It is called a phospholipid because it has this phosphate group. So this diacylglycerol 3-phosphate is going to have the inclusion of one of a number of polar head groups. In class, we talked about choline, serine, or ethanolamine. Keeping in mind that only one of these would be added onto the glycerol group, that would give us our polar head group, and we would have a phospholipid that can be used in a plasma membrane. Exceptional. I believe that is everything for phosphatidic acid synthesis. Looks like it. If we want to get really specific within the cytoplasm, this usually happens at the ER or the mitochondria of some cells. I actually went to Van Fleet and asked for that specifically. That probably won't show up on any exam ever. Thanks so much for listening, and have yourselves a great time.